Section 3.5 deals with one of the really most useful things that a chemist can use, which is percent composition of a compound. Percent composition of a compound refers to what percentage of the mass of a compound is attributed to one particular component or a set of components. To give you an example you can think of, let's say that I'm standing on a scale with a dumbbell, and the dumbbell has, and myself, weigh 200 pounds. If I take the dumbbell and I lay it on the floor and then step on the scale again, and I find that I weigh 160 pounds. What that tells me is that my weight was 160 out of that 200 pounds. So combined, the dumbbell and I weighed 200, but the weight of myself was just 160, which would mean that 160 divided by 200 times 100 would give me my percentage of what my weight was out of the total combination. Pretty much that's what percent composition is in a compound. One of the fallacies or misconceptions of percent composition by a lot of students that I've seen is they try to do it based on atoms. Let's look at our example of sulfuric acid, H2SO4. If we're trying to find the percent sulfur in sulfuric acid, I see a lot of students do the following, and they would say there are 2 hydrogens, there's 1 sulfur, and there are 4 oxygens. And what they do is they try to say there are 7 particles, so sulfur makes up 1/7 of the percent composition, and they figure out the percentage for that. It is percent composition by mass when we do this. So what we have to do is, first, we have to figure out the molecular mass of the compound. So as we learned earlier, to figure out the molecular mass, I break it down. I have 2 hydrogens times a molar mass of 1.0 gives me a mass of 2.0. I have 1 sulfur times a molar mass of 32.1. I have 4 oxygens times 16.0, which gives me a mass of 64.0. When I add those up, I get a combined molecular mass of 98.1 AMUs for sulfuric acid. So that's the total weight. The second thing I have to do is figure out how much the specific component makes up out of that. In this case, I was asked to find just the sulfur. So in this case, the sulfur makes up 32.1 AMUs out of 98.1 AMUs. So 32.1 divided by 98.1 times 100 tells me that 32.7% of sulfuric acid comes from the sulfur. Now let's look at the same problem, and let's say instead I had been asked for sulfate. What percentage was sulfate, not just the sulfur? The sulfate is this portion of the sulfuric acid. So what I would have to do is, I would say this is the sulfate. Sulfate is 96.1, which is the mass of the sulfur and oxygen combined. So since it's 96.1 AMUs, if I were figuring out the sulfuric acid sulfate percentage, I would say sulfate is 96.1 out of 98.1, and I would find the percentage that way, times 100, and I would get the percentage of sulfate. If my formula had 2 sulfates in it, let's say I had, for example, a compound that looked like PbSO4-2, I would have to add up all the sulfates. So again, I would take 2 times sulfur, 2 times 4, 8 oxygens, and I would add all of that up. So when you're finding percentage of something, it's percentage of that entire component in the compound. Let's look at another example. And our example says, calculate the percentage of each element in calcium carbonate. All right, so we're going to have to do several things. The first thing I have to do is calculate the empirical or molecular mass of this compound. So I start off by saying calcium, carbon, oxygen. 40.1, 12.0, and I have 3 oxygens, so 3 times 16.0. All right, so I add all those up, 40.1, 12.0, 48.0, and I get 100.1 AMUs. That's the total molecular mass. That's the first thing I need to do. Now, to figure out the percentage of each component, then, I would simply divide the mass of each component by that total AMUs. And since this is close to 100, what that would tell me is that 40.1 divided by 100.1 for the calcium would give me roughly 40%, probably 40 point something percent. The carbon is going to be roughly 12 and the oxygen would be roughly 48%. Again, we would need three significant figures because that's what we're using in our beginning numbers, but for the sake of our example, you see the point. So calculating percent composition is rather easy. Now, let's look at how chemists actually use percent compositions. And we're going to use this in one of the labs we do a little bit later when we calculate the percentage of water in a hydrate, which is a very common thing we do, and we'll talk more about it at that point. But in our example, we're going to look at how chemists use a lot of this. And one of the things we use is, again, hydrated crystals. When we buy compounds or salts generally are hydrated. If you've been in a restaurant in the summertime, it's really humid, you see sometimes the salts clump together. Maybe in your house you have that happen because it draws moisture. The water molecules actually attach themselves, and we get a hydrated crystal. For example, we have here copper sulfate pentahydrate because there are 5 waters attached to it. So what that means is on every copper sulfate molecule, there are 5 water molecules attached to it. Now, if we want to know how many grams of water there are in 154 grams of that compound, we have to use a percent composition application. So we learned how to use percent composition. Now we need to use how to apply that to a real practical problem. So the first thing we would do, again, is like we did before. We figure out the molecular mass of the compound. So 1 copper is 63.5, 1 sulfur is 32.1, 4 oxygens is 64.0, and 5 water molecules, and notice how I'm keeping the water molecules together, is 90.0. Now, from there, we can simply set up a proportionality. We know that 90 out of every 239.6 AMUs in that compound comes from water. So using a proportionality, we can set that up and say, if 90 out of every 239.6 AMUs is water, then X out of 154 grams would also be water. So it's using our percentage as a proportionality, which is basically what a percentage is. So algebraically, we solve, doing the math, 154 times 90 is 13,860. X times 239.6, cross multiplies 239.6x. And then to solve for x, we simply divide by 239.6 on both sides, which means that 57.8 grams of that compound comes from water. So that means if I put it in the oven and I would dry it off, I would lose about 57.8 grams as I evaporated off the water. Now, let's look at another example in this case. In this case, we're not dealing with a hydrated crystal. We're dealing with simple compound. And in the reaction, maybe we were only concerned with the aluminum. So we're going to take aluminum, and we're going to react it, but we only have aluminum oxide. So we need to figure out how many grams of just plain aluminum there are reacting. So what we need to do first is calculate the empirical molecular mass of Al2O3. So I have 2 aluminums, 3 oxygens. So 2 times 27.0 from the periodic table plus 3 times 16.0 from the periodic table. And I end up with 54.0 and 48.0. Fix that 0 because it looks like a 6. When I add that up, I get 102.0 AMUs. Now I need to set up my proportionality. In this problem, the part that I am concerned with is the aluminum. So I'm going to set up my proportionality with aluminum. Aluminum is 54.0 out of 102.0 AMUs. We want to know then how many grams of aluminum there would be out of 371 grams of Al2O3. So again, we cross multiply. We have 102x equals 371 times 54, which is 20,034. And then if I divide 20,034 by 102, I find that there are 196 grams of aluminum in that sample. All right, so that's one application of percent composition. Percent composition is very useful, and we use it to find, again, or applying it to a compound to figure out what mass of a certain component would make that up. We can use percent composition for many other things. Once you know the percent composition of a compound, One of the things that's useful for that is determining an empirical molecular formula of an unknown compound. We talked about the difference between those two types of formulas back in Chapter 2. An empirical formula, to refresh your memory, is a ratio of the elements in a compound. It simply tells you what ratio there is. So, for example, hydrogen peroxide has a ratio of 1 to 1, 1 hydrogen for every 1 oxygen. Its molecular formula then tells you the exact number of each atom in the compound. Empirical formula is our starting point. If you have an unknown compound, one of the first things you can do is figure out an empirical formula experimentally, and pretty much it comes from percent composition. If I had an unknown compound, I can put a sample of that through a mass spectrometer, which we learned about already. You watched a video clip on what a mass spectrometer was, and you read about what a mass spectrometer was. What a mass spectrometer does is it breaks down the compound into certain components or ionizes them, and it gives you a rough percentage composition of elements in the compound. And from that, we can get a percentage readout. Once we know an unknown compound's percent composition makeup, we can do a reverse process of what we've just been doing and put things back together to figure out what the empirical formula may be. To do that, there's a set of steps we follow, and the steps may not be easy for you to read here, but they are in your book with a diagram, and that diagram is on page I'm not sure exactly what page it's on, but it is in your book somewhere in section 5 or section 6. But it's basically taking this diagram that I have here, but if you can see it or not. The first thing we do is we take our mass percentages and we're going to convert those to grams by simply assuming we have a 100-gram sample, because if you remember, percentages are based on 100. So let's start by looking at an example for this case. An unknown sample is found to have the following percentages: 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen biomass. And we're asked to determine the empirical formula of the compound. So the first thing we're going to do is we're going to take those and we're going to convert them to grams. Now, once we have those to grams, we are then going to use the molecular mass. We're going to divide by the molar mass of each compound or each element, and we're going to figure out how many moles we have. So for the carbon, we had 40.92 grams. We times 1 over 12, we get 3.410 moles of carbon. It is important that you carry out the correct number of significant figures here. Since I had 4 here, I need to carry 4 out for my moles, because otherwise it can lead to some problems. Hydrogen, there are 4.58 grams of hydrogen, so we multiply by the molar mass of 1 mole over 1 gram, which is the same thing, and we get 4.58 moles of hydrogen. For the oxygen, you can see we take 54.50 times 1 over 16, we get 3.406 moles of oxygen. The next thing we do is once we have moles of each substance, what we're going to do is determine what is called the mole ratio. And the way we determine the mole ratio is we will divide all the moles by the lowest number of moles in the compound. In this compound, the lowest number of moles we have is of oxygen, which is 3.406, only by a little bit from the carbon, but still the lowest. So we divide each of those by 3.406, gives us a mole ratio. What this tells me in my compound is my ratio of carbon to hydrogen oxygen is 1 to 1.33 to 1. However, empirical formulas are the lowest whole number ratio, so I can't say my formula is CH1.33L. That cannot happen. So what we have to do, our final step then, is since it's not already a whole number ratio, is we need to change it to an integer. The way we do that is we simply find some number to multiply through by. Now, had our numbers been already an integer values, like 1 to 2 to 1, we would be finished at that step. We would be done there. But since it's not, we need to find a whole number integer, and it's sort of done by trial and error. So we got to try to find some number that I can multiply all 3 of those by to get integers. The carbon and the oxygen obviously aren't a problem. If I multiply by any number of those 2, we're going to end up with an integer value. So what I need to worry about is the oxygen. So we simply do trial and error. If I multiply by 2, I get 2.66, which is still not close enough to assume that it's a whole number integer. In order to be close enough to assume a whole number value, we need to be within plus or minus 0.08. And that's not a hard, fast number, but it's a pretty solid number to deal with. So what it means is if I'm within 0.08 of a whole number, I can assume that's close enough to say, okay, that is going to be a whole number. But 2.66 still is not that case. All right, so if I multiply by 3 then, I would find that my number is 4.02. And I multiply this by 3, I get 3 obviously, and I multiply this by 3, I would get 3 obviously. Now, 4.02 is within that 0.08 range. It's within 0.08 of a whole number or an integer value, so I can assume that this is basically 4, giving me a ratio of 3 to 4 to 3, which means my empirical formula then is C3H4O3. So that's how you determine the empirical formula. Let's look at another example of how we would use that. And in our example here, we have potassium, manganese, and oxygen. When you're given them, you should keep them in the order you're given. So 24.75 grams, I'm going to say, of potassium, 34.77 grams of manganese, and 40.51 grams of oxygen. The next step is to figure out how many moles I have of each of those substances. So I'm going to multiply each of them by 1 over their molar mass. When I find potassium, I find that 1 mole is 39.10. When I find manganese, I find that 1 mole is 54.94. We'll say 0.9 to round to 1 decimal. When I find oxygen, 1 mole is 16.0. Right. From there now, I simply put them in my calculator and solve for the number of moles. So let's start with the 24.75. 24.75 divided by 39.10 gives me 0.6330. I need 4 sig figs and the 0.63299. That second 9 rounds that other one up, which rounds the 2 up, moles. For the manganese, I take 34.77 divided by 54.9, and I get 0.6333 moles. And then for the oxygen, I take 40.51 divided by 16, and I get 2.532 moles. Now that I know the moles of each substance, again, my next step is to figure out how many or what the ratio is. And to do the ratio, I'm going to divide by the lowest number. The lowest number in this case is 0.6330. So divide this by 0.6330, divide this by 0.6330, and divide this by 0.6330. Obviously, 0.6330 divided by itself is 1. This is going to basically be 1 as well. So my calculator then, 2.532 divided by 0.6330 gives me a ratio of 4. And again, it's exactly 4. What that tells me is my ratio of the elements in this compound is 1 to 1 to 4. So from that, I get an empirical formula of K, Mn, both of those 1, but I don't have to write the 1, O4. And that is the empirical formula. Once you determine the empirical formula of a compound, determining the molecular formula requires one other piece of information. If you know from the mass spec the percentages that we said you would, the mass spectrometer can give us relative percentages of the elements in the compound. We just showed you in the last section there how you use those to determine an empirical formula. And we said again that the empirical formula is the lowest whole number ratio of the elements in the compound. The mass spectrometer will also give you a molecular mass or a molar mass of the compound. or an approximate number, and it's usually very close. Given an approximate molecular mass and the percent compositions, we can determine the empirical formula, and then using the molecular mass, we're going to show you here now how you can determine the molecular formula. And as a recap, molecular formula, again, is the exact number of each element in the compound. So let's look at an example. We have a compound and we analyze it, and we find that it contains 1.52 grams of nitrogen and 3.47 grams of oxygen by mass. We figured that out. The molar mass of the compound is determined to be between 90 and 95 grams per mole by the mass spectrometer. We need to find the molecular formula of the compound. Knowing the masses, we don't have to do any conversions at all. We simply already take the masses as they are, and first thing we need to do is determine the empirical formula, just as we did in the last problem. So we take our 1.52 grams of nitrogen times 1 over the molar mass of nitrogen, and we get 0.109 moles of nitrogen. We take our 3.47 grams of oxygen, and we divide that by 1 mole times 1 mole over 16 grams of oxygen, we get 0.217 moles of oxygen. To get the ratio, we divide by the lowest number, which is 0.109 moles of nitrogen. So 1.109 divided by itself is 1. 0.217 divided by 0.109 is 1.99, which is close enough that we can assume that it's approximately 2. Giving us an empirical formula of NO2. All right, so that part we knew how to do already. We had learned that in the previous section. What we look at now then to get from an empirical formula to a molecular formula is very, very simple. All we need to do is take the formula weight of this empirical formula and divide that into the molecular weight or molecular mass given. So we were given that the molecular mass was approximately 90 to 95. The formula weight of our empirical formula we just determined is 46, and I got that by taking 14 from the nitrogen and 32 for the 2 oxygens and adding them together. So to get a multiplier, I simply take 95 divided by 46, and I get approximately 2.06, which is about 2. In this case, I used the higher number, and it's always better to use the higher number and then round to the nearest whole number when you get your answer. So what that is telling me is that my molecular formula is roughly 2 times greater than my empirical formula. So all I would do is simply take that number and multiply it through my empirical formula. So I take NO2 and I multiply everything by 2. So N is 1 times 2, I get N2. O2 times 2, I get O4. So we say our molecular formula then is N2O4. Let's look at again another example. A compound is determined to be 78.26% boron and 21.74% hydrogen. If the molecular mass is about 28 grams per mole, determine the empirical and molecular formula of the compound. So we have to determine both things. First, we have to determine the empirical formula. To do that, I take my percentages and I change those to grams. So I have 78.26 grams of boron, and I have 21.74 grams of hydrogen. To get moles, next, I multiply by 1 over the molar mass. So for the hydrogen, 1 mole is 1 gram. And for the boron, 1 mole is 10.8 grams. Using my calculator again then, I simply plug it in, 78.26 divided by 10.8 gives me approximately 7.246 moles of boron, and I would have 21.74 moles of hydrogen. Now, mathematically, if I take and divide by the lowest number of moles, my lowest number of moles is 7.246. So I divide this by 7.246 and divide this by 7.246. And it gives me a ratio of 1 to 3. So my empirical formula determined experimentally is BH3. Now, to get the molecular formula, I need to take a molecular weight given, which was about 28. and I divide that by the formula weight from this compound. So 10.8 plus 3 is 13.8. 13.8 is basically 4. 28 divided by 14 is approximately 2. Which means that my molecular formula then is 2 times greater. So my molecular formula would be B2H6.